It's a crucial test.
Electrical has one small issue with the emergency shutdown solenoid, but that can be bypassed manually to ensure everything is good. Other than that, we're ready to go.
For a major project.
Okay, we're ready when you are.
Power pump one, start up.
Today marks a milestone in one of the biggest engineering feats ever attempted in Metro Vancouver.
We're about to fire it up.
This is the story of the Seymour Capilano Twin Tunnels project. Metro Vancouver's drinking water ranks among the best in the world. It is delivered daily to over 2.4 million residents in the Lower Mainland. Our drinking water is treated in modern, world-class water treatment facilities. And in May of 2015, the final component of this robust system has come online.
Cheers to clean drinking water in Metro Vancouver.
There's no champagne in these glasses, only pure mountain fresh water. It's a toast to the end of construction for the Seymour Capilano Twin Tunnels project. Years in the making.
Why filtration is necessary is because even when we chlorinate and disinfect our water, which can kill bacteria and viruses that could get into even a protected watershed, that chlorination won't kill parasites, which can cause human illness. And there can be events in the watershed where silt and mud is washed into the watershed and chlorination may be less effective.
You could say the actual start of the Twin Tunnels project was over 100 years earlier, when the need for a municipal water supply was made clear by a message written in flames. The city of Vancouver was only 2 months old. In just half an hour, a fire wipes out the newly incorporated town, claiming dozens of lives, burning nearly every building in the town site, and highlighting the need for a municipal water supply.
One of the problems when Vancouver did burn to the ground was that there was no reliable source of water to be able to put the fire out.
The Vancouver Water Works Company is formed. The company takes $250,000, about $6 million capital in 2016 dollars, and delivers on a promise to bring fresh water from the North Shore to Vancouver. After surveying the streams emptying into Burrard Inlet, the company decided the Capilano River offers the best option for supplying Vancouver with water. First, a dam was built on the Capilano River, and then, after an unsuccessful first attempt, a pipe was laid across the first narrows to Stanley Park. The system fed a network of 16-inch water mains in the city and went into operation in April 1889, discharging more than 42 million gallons a day. But even then, engineers and planners were looking to the future. Engineer Henry Badley Smith, who chose the Capilano as the site for the first reservoir, made this prophetic comment about the future of the region's water supply. It may be that people at some future day will cause a dam to be constructed across the narrow gorge and once again convert this valley into a lake. Vancouver will then possess a reservoir from whence to draw its water supply, which will not be surpassed by any waterworks system on the continent. 6 decades later, the Cleveland Dam is completed in 1954, fulfilling his vision of a reservoir on the Capilano. Water supply infrastructure continues to grow along with the region. In 1961, an upgraded dam replaced the original 1927 version on the Seymour River, and the 2 reservoirs, along with a third in the Coquitlam watershed, form the basis for today's system. For decades, this robust water supply network met the challenge of supplying clean drinking water to a growing Lower Mainland. By the end of the 20th century, Metro Vancouver faced new water quality requirements from federal and provincial governments, calls for lower turbidity from medical health officers, and the looming demands of a region projected to grow by 1 million people in 25 years. The decision was made to embark on a major water filtration project.
The federal government, I think, was responding to the Walkerton situation and concerns about making sure that they had standards in place across the country that ensured healthy water. And so we anticipated those regulations coming down, and we changed course and introduced filtration, and it proved to be the right decision.
It was the last piece of the puzzle that we needed to make sure that we were doing everything we could to protect the drinking water. Many years ago, even with very good water treatment, we did know that at times of turbidity, there were increased visits for gastrointestinal illness at some of our hospitals around the Lower Mainland.
The decision to build the filtration plant did not come easily. The original plan for a public-private partnership was abandoned, and the decision was made that Metro Vancouver should be the operator.
And it would lead back into Seymour Main number 2, correct? He's convinced that'll work.
Oh, that's it.
Early on, the engineers and designers knew they faced a daunting task. Plans called for one massive facility to treat the water from both the Capilano and Seymour reservoirs.
After we did a very detailed assessment of all the social, the environmental, the economic, and the technical factors, it was determined that a combined plant built in the Lower Seymour Conservation Reserve that would treat both the Capilano and the Seymour sources was selected as the preferred option.
Their solution was an ambitious feat of engineering, making it possible for the filtration plant to treat water from both reservoirs.
In the history of the GVRD supplying water, it's the largest project we've ever done. The tunnels are a real challenge, but first we have to dig a large diameter shaft, 40 feet in diameter, down about 500 feet before we can even bring the tunnel machines onto site.
The Seymour Capilano filtration plant, once completed, needed to be the biggest water treatment plant of its kind in North America. It was designed to meet LEED Gold certification, providing advanced ultraviolet water treatment technology, and to deliver 1.8 billion liters of water daily. The tunnels would make it possible to blend the waters from both reservoirs to manage the region's water supply. But first, it had to be built. The first hurdle turned out to be a very small frog.
There was interest from local environmental groups that the frog habitat that this represented was not found elsewhere in the Seymour Valley. So redesign was done such that we could compress the northern end of the filtration plant and the associated construction, and we were able to save this area.
Adjusting the location was just one aspect of how sustainability was integrated into every aspect of the design.
One of the things that we decided to do was to invite groups in to salvage the plant material on the site. Once the filtration plant is built, we will be able to revegetate a certain portion of the site, and the intent is to return it to a state that's as similar to the surrounding forest as possible. So we're planning on revegetating with native materials.
By 2006, the filtration plant was taking shape.
Well, right now we are inside the clear well, which is one half of the two systems that we have. This facility itself will house 200 million liters of water, and the overall plant will produce 1.8 billion liters of water per day. That's enough to actually fill BC Place Stadium within 1 day of production.
In spring 2008, Seymour reservoir pipes were connected to the filtration plant, requiring a rare shutdown of that water supply. In order to keep the water flowing, a complex rerouting of other reservoir sources ensured that Metro Vancouver residents didn't notice a thing. By the end of 2008, the filtration building was nearing completion and testing had begun. As the filtration plant took shape above ground, work was taking place on the tunnels below.
We've sunk the vertical Seymour access shaft, and there's quite a substantial cavern at the shaft bottom.
The shaft is 11 meters in diameter and 180 meters deep.
It was also sunk without any major accidents, which is an outstanding safety achievement. In addition to the shaft, there's quite a substantial excavation at the bottom of the shaft.
Workers take an elevator to the bottom where the temperature is a constant 6 degrees. At the bottom of the shaft, a perpetual rain falls as a result of the cold air from the surface meeting the warmer underground air. The work proceeds under the watchful eye of the patron saint of miners, St. Barbara. In her hand is a Davy lamp, which was used to detect methane in the early history of mine work. Once the excavation at the bottom of the shaft was complete, boring machines were lowered into place and the drilling of the tunnels could begin. The project called for two 3.7-meter diameter tunnels to be drilled 7 kilometers below the North Shore Mountains. from Seymour to below the reservoir at Capilano. Special diesel engines with scrubbers to reduce emissions carry the workers from the base of the access tunnel to the boring machine.
We are in the passenger car of the train that's all its way from the Seymour shaft to the front of the excavation. The excavation front is approximately 4.8 kilometers from the Seymour shaft. This train ride is going to take us approximately 20 minutes.
The work goes on 24 hours a day, 2 shifts of 10 hours for the boring and 4 hours for maintenance.
It's way too high of a gauge in there anyways. It'll surely be at 50 or 60 psi.
The tunnel boring machines are 600 meters underground at this point, just a little bit west of Grouse Mountain.
This is the tunnel boring machine, approximately 18 meters in front of us. There is a cutter head that actually excavates the rock. The cutter head turns, it crunches the rock gets scooped up and it gets put into the conveyor belt. The conveyor belt takes the rock to the back of the machine where it gets dumped into those cars.
The boring machine has large grippers on either side.
In order to move the machine forward, we need to apply the huge amount of force to these grippers into the side wall that allow us to continue excavation forward.
Boring these tunnels through solid rock demanded the brute force to crush rock and the precision to mark every crack and crevice along the length of the tunnel. Rail cars carry the granite from the tunnel head to be dumped into the muck bucket to be hauled to the surface. Every day about 67 carloads of granite are excavated. Each train load is 5 cars and equals 1.5 meters of progress. One challenge with any excavating project is disposing of the tunnel material, or muck as it's called. The Seymour Capilano project found a way to use the material and make a place for Mother Nature.
We're in the Lower Seymour Conservation Reserve and we're 4 kilometers up the valley from Rice Lake. This area was a gravel pit in the past. It was used for the construction of the Seymour Falls Dam in the early 60s. And it was a good site for current construction activities.
All of the waste or spoil material that was excavated or mined out of the tunnels between here and Capilano Lake has been stockpiled in here.
Using this site had a big impact on exhaust emissions and heavy vehicle trips in the community. It's estimated nearly 50,000 dump truck trips through the North Shore were eliminated by choosing this location.
That's what we're trying to achieve here, is a little bit of everything, partially reforested, an open wetland area that provides habitat for different bird species, place for animals to water, as well as the open grassland, which will provide grazing area for black bears and the deer species that we have in the valley.
Green roofs are another feature of the filtration plant, both over the main building and the massive clear wells.
We've got 2 different green roof systems that we have here, the one that we're standing on right now, and then there's also one on the roof of the building. The ones on the building roofs are extensive. The soil depth is quite a bit less. It's more like a garden planter that you would sort of have on your balcony. We put soil on top of the roof, and that helps to stop the amount of water or runoff that we have to deal with. It's quite a big area, and we've planted native plants here to use that water and the nutrients in the soil.
The large green roof covering the clear wells will be open to the public for recreation. An interpretive trail around the filtration plant lets the public enjoy the natural setting.
As you work your way around the trail, you'll be able to see the green roof that was built on one portion of the plant. You'll be able to get up on the clear wells itself. You're going to come around the other side and you can see some of the stormwater ponds that were created so that there would be no net gain in water leaving the plant.
The interpretive trail is about 2 kilometers long and circumnavigates the entire filtration plant.
We are going to be running our school programs through it, so kindergarten to grade 12 education programs come up here, and we'll be using that interpretive trail for those programs. So yeah, it'd be good for everyone.
The spring of 2010 marks the beginning of a new chapter in Metro Vancouver's drinking water history with the official opening of the Seymour Capilano filtration plant.
The Seymour Capilano filtration plant is truly a shining symbol of Metro Vancouver's unwavering commitment to sustainability in our region.
The reusable bottle.
Let me say, ladies and gentlemen, it is a pleasure to be here on such a historic occasion. The Seymour Capilano filtration plant project is a testament to engineering ingenuity, professionalism, and very, very hard work of our employees.
The end of the tunnel boring portion of the project is marked by the breakthrough of the tunnel boring machine connecting the 2 tunnels at the Capilano end. The next phase in the project was the excavation of shafts to the surface. In late winter 2011, the first surface breakthrough of one of the shafts took place. To excavate this shaft, a raised bore system was used. A powerful drill first creates a narrow pilot hole that meets the tunnel below. Then, a 4-meter cutter head is attached to the drill. The raised bore pulls upward, with the cut rock falling down to the tunnel. The breakthrough is a significant moment for everyone.
For us, it's quite exciting because it represents completion of a big project.
It takes about 2 hours as water seeps through the cracks. The reamer has mere inches to go. The work crew watch as cracks appear on the shaft surface. A few photos, smiles, then work resumes. Meanwhile, the detailed finishing work on the tunnel is taking place. This phase of the work is called shotcreting.
In summer 2011, approximate period 6 months. Last 6 months, the contractor has been doing the shotcrete work. It is basically same as concrete. The difference with shotcrete is it's shot onto the wall and stays on the wall as a lining material.
In 2012, installation of the steel linings for the tunnels began. Each morning, the focus shifted to Anasis Island, where 680 sections of tunnel liner were stored.
This steel pipe liner has been designed to be installed in both ends of the tunnel.
In proper order, the liner sections were lifted by a machine commonly used in log sorting yards. Each liner weighed 31 tons. Every workday, 4 would be trucked from Delta to North Vancouver via the Ironworkers Memorial Bridge. The process wasn't much different in the early 1950s, when large valves had to be trucked to the Cleveland Dam construction project on the Capilano River. Far fewer vehicles were on the road then, when the load traveled through Vancouver and over the tolled Lionsgate Bridge. Once they arrived at the work site, the installation crews took over.
I've never experienced something like this before, dealing with large pipe and sinking it 600 feet into the ground.
Inserting the long liners took some planning.
That belly strap enables you to pick it up flat, and then your winch line enables you to vertically get the pipe into the right position. It's just a combination of a lot of things and a little bit of fear because you're dealing with 70,000 pounds.
Below ground, another team took over.
And hold there.
The pipe was prepped to travel almost 7 kilometers on miniature rail platforms through to the Capilano end. Liners were also being installed at the Seymour end of the twin tunnels.
It's been a good project. I got a good crew, and that's the major part of it.
On January 31st, 2014, the last tunnel liner section was installed.
It's all slow and steady, and that's the way we like it. In the future, it's something we can tell our grandchildren.
As much as 150 million liters of water will be pumped from the Capilano Reservoir through the raw water tunnel to the filtration plant every day. Overcoming the increase in elevation between the two locations requires a lot of energy. The return trip, however, uses gravity to move the water. An energy recovery facility will take advantage of the excess pressure that process creates to power an energy recovery turbine that generates electricity.
Well, the power of the generator is almost 1.7 megawatts, and according to the flows that we've seen historically, we're expecting to see 9.6 gigawatt hours of electricity produced every year.
Once the twin tunnels are fully operational, the energy recovery turbine will be used to offset some of the power requirements for the Capilano raw water pump station. The water pressure, which makes it possible to spin the turbine and generate power, must be dissipated before the treated water can flow into the Capilano water main. A large breakhead tank under the energy recovery facility reduces the pressure of the water before it reaches the distribution system. In February of 2015, one of the most important tests of the twin tunnel system heralds a milestone for the project. For the first time, these 8 massive pumps will move raw, untreated water uphill for 7 kilometers from the Capilano Reservoir to the Seymour filtration plant.
Discharge and inlet, and we have extra ones on standby.
Oh, perfect. Do you want to start?
Engineer Adeline Chin is today's project lead.
The objective to today is just to confirm operation readiness at the pump station and at the SCFP.
They are talking to the team at the other end of the tunnel at the Seymour filtration plant.
Yeah, we have a sample pump running and the instrumentation is calibrating the meters as we speak.
The checklist had a bunch of prerequisites that we need to make sure was completed before we can start the pumps. It was well thought out.
What should happen is a computer notifies an in-house electrical system to send more than 4,000 volts of startup power to multiple sensors and motors. A butterfly valve that's almost a meter across will slowly open while the 2,000 horsepower pump kicks in.
There were so many things, so many factors that were contributed to it. We were wondering, well, which one should we start first?
The checklist review continues and is looking good until the Seymour end spots a problem.
Hey, Adeline, can we, sorry, we're just double checking on the flow meter.
Flow meters are at both ends of the tunnels. The readings need to match.
The flow meter, is that, I'm sorry, is red.
Flow meters are just one of the 53 items on the pre-test checklist. What can't be controlled are natural events.
We had a lot of rain this weekend, so I thought, oh my goodness, if we had a landslide and the turbidity was high, then it would be like canceled, but it all worked out really well.
Weather and land have cooperated, and the flow meter display issue is resolved.
Electrical has one small issue with the emergency shutdown solenoid, but that can be bypassed manually to ensure everything is good. Other than that, we're ready to go.
The crew take their positions at the pumps, 4 floors down in the base of the building, and the electrical panels that fill an entire floor. At the Seymour end, crews stand by in their control room, at the initial outflow, and a secondary receiving pond.
Okay, we're ready when you are.
Pump 1 start up. Over. Standing by.
A humble mouse click will activate the process.
I understand when the pump starts up, it's pretty loud. So we'll hear the and then transfer over and the water whooshing.
Okay, ready for pump 1 start.
Pump number 1 is fired, and it faults.
There's about 15 interlocks, and if any one of those goes wrong, the pump either stops or it won't start.
The electrical team goes to work to try and find pump number 1's fault. Installed several years earlier, the form variable frequency drives and the switchgear with over 12,000 volts have sat waiting for this day.
All right, we're about to fire it up.
The team decides to try the next pump.
Standing by.
Okay.
Again, a fail, but of a different sort.
Drive check.
That one little device took down the entire pump and stopped everything.
With 2 down, they plan to try a third. Third time's a charm.
They got a valve is opening at 6%.
There you go.
Yes, we got flow. Yeah, we are showing flow increasing here.
Everything's looking good so far on our end.
Excellent.
I was really excited but nervous at the same time. We ran it for 15 minutes up and 5 minutes running and then 15 minutes ramp down. It was successful.
First time we've transferred water from the twin tunnels from Capilano Dam.
It went fantastic. Glitches, there's always going to be a little problem here or there, but we'll work them all out.
1 month after the successful raw water testing, the Seymour Capilano Filtration and Twin Tunnel Project enters the home stretch. A small crowd gathers beside the Capilano Reservoir. They are here to witness a momentous occasion.
It's a real big day. We're seeing water behind me that was originated here in the Capilano Reservoir. It was sent to the Seymour Capilano Filtration Plant. It was filtered. It was UV disinfected. There's a bit of chlorine added, and it came back a separate tunnel to here. Now it's being discharged. So right now you're seeing water that's basically being flushed out as we clean out the tunnel.
This is an important test of the spillway. It's only intended to be used in case of emergency, so these activities today offer a unique opportunity to see it in action.
So we're almost 50% through the flushing as we speak, and everything's going as planned. Everyone here and their expertise is making this day go exceptionally smoothly.
I feel fortunate that I joined Metro Vancouver at the best time because I had the opportunity to see the completion of the project. I actually had the opportunity to walk through the tunnels and get a sense of the scale. It is an unbelievable team that has put such high standards on themselves and set the bar very high on any other project that Metro Vancouver takes on. They have just done a remarkable job.
My over 35 years of my professional engineering career, I haven't had the privilege of working with a team like we had on this project. They were amazing. I should also acknowledge our former water committee and our utilities committee, as well as the board, supported us every step of the way.
I can't say enough about how great the engineers and the entire team over the last 10 years came together to make this work. It's been a lot of work, but they're very proud today, and rightly so, because, you know, we're going to have a great quality of water here for generations to come.
great quality water. It's been a part of our history for more than a century. And with the Seymour Capilano Twin Tunnels and Filtration Plant, it remains a part of our present. Perhaps most importantly, it's our promise to the future.